So let's start with this. We're going to first talk about the scientific definition of work, not what work is. Like work, obviously you go to work every day. That's not the work we're talking about here. We're talking about when you do work on an object. When you do work, even though it sounds weird, you do work on an object. Second, we're going to identify when work is actually being done. And third, we're going to calculate what's called the net work on an object. The net work. Okay, so let's start first with the definition. So scientifically, the definition of work is simply the product of the component of force and the displacement. And why do I put cosine theta? And let me explain this. So it's the product of force and displacement. We're talking about these two variables here and here. But this cosine theta, it's because we're looking at the force that's along the direction of the displacement. So let's say, for example, is an easy way to show you this. You're pulling on a shopping cart, and the angle that you're pulling at is 25 degrees. You're pulling with a force of 50 newtons. So free body diagrams aren't going to go away. That idea is still necessary here. Now, which way does a shopping cart move? Does it move up and down or left to right? Left to, I hope so, right? It should move left to right. So let's say in this case it's moving to the right. I don't know what the acceleration is, but I'll put motion. The motion is to the right. Now, if I look at the definition of work, it's the product of the component of force along the direction of displacement. Let me highlight that real quick, because that's the key here. The component of force along the direction of the displacement. And what you're getting from that, let me make this smaller so you can see a little better, is really F times cosine theta. Where do you remember using F cosine theta? When do you use F cosine theta? Okay, so it's not VI in this case. What is it in this case? Instead of velocity, what are we applying? A force. It's really, if you think about it, we think about this force, it's really pulled this way, and it's pulled this way. Right? That's what that means. Remember, when something is pulled at an angle, it's pulled up and to the right. So we only care about the component of force that's going in the direction of motion. Is motion up or is motion to the right? Which way is motion in this problem? To the right or up? To the right. It's definitely to the right. So all I care about is the component of force that's acting to the right there. So here is the force that we care about, Fx. And if you remember, Fx is really F cosine theta. So if you look at the formula, and you go back up here, you'll see this is F and this is cosine theta. So this formula, although it's written as Fd cosine theta, the reason it's written that way is because we're thinking about the direction of motion to the right or left. Now, it could be up or down also. So the actual angle itself, theta, is the angle, this is a little bit different than last chapter, the angle between the force and motion. Not necessarily the angle that we're shown here. Because if motion were up and down, the angle we would use would end up being 65 degrees, the complement of that. Again, if motion were up and down, it means motion would be this way, the force would be this way, this would be the angle that we would use right here. I want you all to understand that. If motion were up and down, that's this. If the force is this way, it means the angle between them would be 65 degrees, it turns out. So the angle is a function of motion and the force. Again, the angle is a function of the direction in which you're moving and the direction of the force is applied. It's always the angle between those two vectors. Okay, this vector is acting up, this vector is acting up and to the right. This would be the angle if this object were being pulled off the ground. It's not, though. It's being pulled to the right. So since that's true, motion is this way, the angle is this way. Here is the actual angle. The vector is this way, the angle is right here. So again, this makes sense to use cosine theta. Even here, we're going to use cosine theta also. Okay, so our definition for this chapter is going to be Fd cosine theta. This is a new unit. You haven't used these before, so write them down. Unit of joules, Joule, joules. And it's a product of Newton times meter. Okay, a product of Newton times meter. And you know that because you look at the formula. The formula is force, which is measured in newtons, distance, which is measured in meters, cosine of angle, cosine of whatever theta is the angle, has no units on it. So we know that Newton times meter, and that's going to be a joule. Any questions so far? Yeah, Ernest.
Except for horizontal, we still can use F cosine.
Even if it's vertical motion, we're still going to use f d cosine theta, but the angle would be the other angle then.
Okay.
Does that make sense?
Yeah.
Okay. Instead of having you memorize sine and cosine for this one and use that each direction, you could always just use the direction of motion and the angle and the vector itself and use the cosine. If you wanted to, though, you could use sine of 25 because that would give you this force, wouldn't it? So you could do that also. You could use f sine 25 and use this angle. But if you can use f cosine, use this angle here if you're going upward. Turns out you're going to learn about that in math because the sine of 65 equals the cosine of 25. It's kind of a weird thing. When angles are complementary, their cofunctions are equal. So 30 and 60 work.
What does that say after an angle?
Between. Yeah, so if you had like a 80 degree angle and a 10 degree angle, the sine of 10 is equal to the cosine of 80. It's always going to work that way. You're going to find out about that in math this year. But it's something that you'll see here if you try it. So I have a question for you. Let me give you an example, all right? I'm pushing on this desk. I'm pushing. Is it moving it? No, it's not moving. I'm pushing really hard. How much work am I doing? A lot of work, right? A ton of work. But scientifically, how much work am I doing? None, because there's no what? Movement. And the formula has distances in it, doesn't it? So what's the distance traveled if I push and it doesn't move? So it turns out that scientifically work is different in definition than what you think of work. You see what I'm saying? So it's very misleading to say, if I'm standing here holding this iPad, it takes me actual effort to do this, doesn't it? But am I doing any work? No. The iPad is not moving. If I did this with like weights, if you lift weights, you're doing work because you're making those weights move a given distance. You're applying a force over a given distance. Whereas here, you're just holding that object at rest. You see what I'm saying there? So that's a great kind of like, those multiple choice questions that you think it's like, I'm just going to multiply them together and the answer just has to be 0. That's the kind of question you could expect. Like on the last test with the acceleration being 0, that question. That's where you can see that.
What about like if you do a cardio and you go up and you end up in the same place?
Well, this is distance, not displacement. That's a great question. So you hear the question there? Imagine you're lifting weights, right? You hold the weight here, you lower it, and you raise it back up to the place it started. There's no displacement at all. It started here, it ended here. But this definition, or this formula, uses distance. And remember, distance would be the sum of both of those lengths being positive. So say a foot down and a foot up. So 2 feet would be the distance traveled when you do one curl. Okay, it's a great question. These are questions you should ask, please. If you're wondering about stuff, you have to ask those questions. Because if you're wondering, somebody else probably is too. So let's look at the first example. Really simple. Okay, really simple. You're just applying it directly to the formula. What are the odds? I didn't even read these notes ahead of time. I wrote these notes like 4 years ago. Shopping cart. So how much work are you doing on a shopping cart if you pull 12 meters, if you pull it for 12 meters with a force of 75 newtons at an angle of 60 degrees? If I'm not giving you anything about the angle like above the horizontal, you could assume it's between the direction of motion and the force itself. Okay, you could assume it's between the direction of motion and the force itself. And think about how you would pull or push on a shopping cart. Have you ever pulled on a shopping cart before? When I was a kid, my parents used to do it, I remember, because you'd want to sit in the top, they would always pull on the front of it. And my brother would end up standing in the back and make sure I didn't fall out. Just to make sure I didn't end up going in the wrong direction. So if you pull on it, you would pull like this. That's how you would pull on it. So the same way we drew the diagram earlier. If it were a push, it really wouldn't be any different. Okay, if it were a push, so this is the pull, here's the direction of motion. There's the 60 degrees. If it were a push, it would be this. And that would be the direction of motion, and it would still be 60 degrees. So if you want to consider this a push or a pull, it doesn't matter. I need you to see that these are interchangeable in this problem. It doesn't make a difference. So the force is at an angle. The direction of motion is horizontal. The force is 75 newtons. It's interesting to notice that it doesn't matter what the mass is. The mass of the object doesn't end up playing a role here. Unless you're solving for the force maybe, and then you use the force to calculate the work, maybe then you would need the mass of the object. But here, we don't need the mass of the object. We know that the distance traveled is 12 meters. We can take F times D times cosine of theta. That's 75 times 12 times the cosine of 60 degrees. Cosine of 60 turns out to be a half. Half of 12 is 6. 6 times 75. 450, I'm guessing. Is that right? It's kind of simple math. The reason is cosine 60 turns out to be 0.5. That's an angle you'll learn at the end of the year that you're going to want to memorize. Okay. Let's change the problem up now and visualize. Any questions on this? The math behind it? It's really pretty simple math. That's what I was saying before. Like the math in the beginning is going to be really pretty easy. As we get later in section 6.2 and 6.3, it's going to get a little more complicated. So the force applied, how far it's traveled, the distance, 12 meters horizontally, and the angle between the distance traveled and the force at 60 degrees right there. So what if this problem had been instead of, I'm trying to think of a good way to put this. Instead of being pulled along the ground, I don't think this is possible. I guess it could, yeah. What if it's being pulled vertically? Imagine there's an actual structure here with bearings here. So that this object, even though it's pulled at an angle, will rise vertically like that. So imagine now you have like there's a worker up here, or there's a machine up here, and the machine up here pulls on some sort of a pulley. It pulls it around these bearings, and the object slides up the wall, but it's being pulled at that angle. How would this problem change? It still moves 12 meters, let's say. Still moves 12 meters.
But like last time I asked, you said that once you do like sine 60.
Yeah, you could do sine 60, or what else could you do? Where would the angle be?
30.
Yeah, so you can think of here as the direction of motion. Here's the force itself being applied, so you use an angle of 30 degrees instead. I want you to see the difference between the two possibilities. If it's moving horizontally like it was before, there's the angle of 60 right there. But say it's the same diagram, and suddenly part B says, now it's being pulled vertically along these roller bearings along the wall, and it's being lifted up until it comes over that. So maybe you're like lifting coal out of the ground. This is actually what they used to do with horses. They would attach horses to like a mine shaft or a shaft, and they would haul coal up there, and they would have these bearings along the side which would reduce friction. Horsepower came about from the amount of coal it could lift in a given time. Like these are all the actual etymologies of these units and stuff. But this is an example of it being moved upward, yet the force is at that angle, so this angle now we would use would be 30 degrees. That's all that would change there. Okay? Questions on that? The idea? All right, the next thing I want to talk about is the concept of an object being pulled, but friction acting against it. Okay, so what would the angle theta be if a force is a horizontal force in the direction of displacement? What if it's in the opposite direction of displacement? So for example, if it's in the direction of displacement and the force is horizontal, it means displacement is horizontal. This is the first scenario. And the second scenario is this. The force is acting in the opposite direction of the displacement. So we've got scenario 1 and scenario 2. First, think about it logically. Logically think. If an object is being moved this direction and it's being pulled this direction, you're probably applying the force to help its motion. Agreed? Okay, now, what would oppose the motion of an object? This would be friction. What do you think, work-wise, would be the difference between you doing work to help the object versus friction doing work to hurt the object, to reduce its motion? How would it change? What do you think? Hypothesize. Take a guess at what you think might happen. What would happen to your answer? I'm giving you a hint by not asking for an exact number, by saying what would happen to the answer. Not a decimal, but good idea. You want to take a second stab? What? Not a fraction? It would be negative. The idea of that not being a whole number instead of being positive being negative is similar, right? It would be negative. So it turns out because of the angle. That's the reason. So what's the angle between the force and the motion in the second diagram? Not the first diagram. The first diagram it's easy, but it's not obvious. The second diagram, it's obvious the angle here. What's the angle? 180. You learned this in geometry last year, a straight angle or straight line. has an angle measured of 180. That's the angle between the motion and the force. What's the angle between the motion and the force in the first diagram? Or, not 180, it's 360 or something else. Not 90 would be like this, right? 90 would be the force is this way and the motion is this way. That's 90 degrees. 0. This one would be 0. So you could use 360, but I'll explain, or you'll learn about that this year in Algebra 2 Trig, why 360 and 0 both work, actually. But for now, let's just say 0. But 360 does work, Ryan. Ryan saw it as like, oh, you loop around, right? And there's 360. And that works too. We're going to say 0 degrees for now. I can't really draw that in the diagram, so I'm going to write it instead, right? If my motion is this way, and the force is this way, then clearly there's no little space to draw the angle theta in, so always write it in the diagram. You can't really see that, so it's obvious. So go ahead real quick in your calculator. Type in cosine 0, type in cosine 180. Try them both. Try them both. And I want you to not only give me answers right now, but explain the nature or the reasoning or the physical significance of why your answers make sense. In the context of this problem, I mean. Not necessarily like mathematically, but in this problem. Why would it make sense? Right, go ahead. Explain. What did we just talk about, right?
Oh, yeah. The friction is acting on the
Yeah, in the formula, we're going to have to use cosine of theta. It's FD cosine theta. So you can easily conclude from this that friction does negative work on an object. You can write that down if you'd like to, if you haven't already done it. Right, in the second example, negative work is being done on the object, therefore it is slowing down. If you do work on an object positively, you are speeding it up. Again, if I pull on an object like this, I'm making it faster. So when I do cosine of theta in my formula, it's going to remain positive. I'm doing positive work. When an object is sliding across the table like this, and it comes to rest, it's because friction is pushing that way against it, therefore hindering its motion or acting against this motion in case 2. And so friction is doing negative work in order to slow it down. Yes? We're going to talk about that in the next one. Yeah, it's whichever is bigger will be the overcoming one. So if there's a force to the right and a force to the left, you just sum them together with positive to the right, negative to the left, just like last chapter. Okay? Whichever force is greater is the force that will do the most work. Therefore, the net work, like net force, is what we're going to talk about in a minute. All right? So friction does negative work. Any questions on this? Does it make sense? Again, negative? Okay? Because it's negative here. The only time we're going to use an angle that's greater than 90 is going to be 180. We're not going to be doing like cosine 135, cosine 155. Those would all be negative also, but we're not. Anything beyond 90 to 180, cosine of that is always going to be negative. Again, you'll learn about that this year in your trig course. It's in the 4th quarter you start to do Algebra 2 trig, or the trig portion. So cosine 180 is always going to be negative 1. That's something good to remember, by the way. Okay, it should be something you should know by the end of this chapter for sure. It's be like, as soon as you problem with that, you know right away. So here's your example. I don't really need to go into real detail about it. But take a look. If you apply force to the right and it's moving to the right, in both of these diagrams, you see it's positive work. The force is to the right in some sense, right? It's up and to the right. And in the second scenario down here, it's down and to the right. So these are both positive examples of work. But here, imagine for some reason that this object we're moving already, it's moving and you grab that rope, right? See there's like a rope attached here? So imagine the object is moving already and suddenly you're able to grab onto that rope and stop it. You would be doing negative work because you would be lowering its velocity. You would be like friction in a sense, pulling against its motion. Or, again, the car's coming towards you, what do? You push against it to stop it. So you're stopping it, so you're lowering its velocity, you're lowering its motion, so you're doing negative work again. So in these cases of negative work, these are analogous to friction. Even though it's a person pushing against the motion, it's analogous to friction. So when a running back is running and the linebacker goes to tackle him, he does negative work on the person, if you think about it that way. He slows the person's motion down. Okay? He lowers the person's motion.
Negative work doesn't necessarily mean you have to move in the left direction.
Technically, to do negative work, it should be over a distance. The force should be applied. So if you think about it, ready? It's moving this way, but it's still a distance. Whatever this distance is, friction acted over that distance. It doesn't have to move the other direction. The force has to act in the other direction. Okay? Because even though it stops when it hits your hand, for a little bit you do work while it's moving still, technically. It's a weird one with the hand. With the friction, it makes more sense. So let's take a look at this concept of net work. This is what John was asking about. This is our last example for today. So imagine you have a desk and you're pushing on it with a force of 20 newtons. The desk's weight is 20 newtons and you're pushing with a horizontal force of 12 newtons and it's going for a distance of 24 meters. If we know the coefficient of kinetic friction is 0.2, that's remember mu from last chapter, we want to calculate three things. How much work is done by the student? How much work is done by the floor in terms of what friction, right? The floor. And what is the net work done on the object? So we can do this two ways. We can find the work done individually and then sum those together, one being positive, one being negative, to give us answer C. Or at the end of the problem, what we're going to see is that we can think about the force to the right and the force to the left are kind of canceling each other out. So if we could find friction and subtract it from the pull of 12 newtons that you're giving it, then we could find the overall force and just use that to calculate part C, which is the overall work. How would you figure out the first part? Part A. How much work is being done by the student? This is pretty easy, this one. What's the definition of work? What's the simple definition of work, formula-wise? What's the definition? What do you have? Yeah?
Force times distance times cosine angle.
Force, distance, cosine, angle. Very good. Now, we're told that the desk has a weight of 20 newtons. How do I know that's its weight? What would we measure if it was mass? Kilograms. Yeah, the mass is always measured in kilograms. So a student pushes a 20 newton desk. 20 newton is the weight of the desk. So that's not needed right now. Is that clear? Because a lot of you see newton or you see a unit. You've been doing a good job with this with units, but then you're mixing up which is for. So the 12 newton is what we're going to use now because look, it says with a horizontal force of 12 newtons. That's the key. That's what we're looking for. We're going to use that. So let's take that value and plug it in for our force. The distance it travels is 24 meters. That's given in the problem as well. Now, what is the angle? I don't see anything about an angle given here. What do you got, Gabe?
0.
Why? Horizontal, okay? Again, if you didn't know this and you wanted to draw a free body diagram, that might be useful. If you drew a horizontal force to the right, you would see that the angle is 0 degrees because the motion is also to the right. There's motion in the dashed blue, and the force is that solid black line. Okay, again, force, motion, both at the same direction, therefore theta is indeed 0. So 12 times 24. 12 times 12 is 144, so double that. 288. Okay, my units are joules. I remember that because a newton times a meter in this chapter is defined as a joule. A newton times a meter was defined as a joule. That's part A. It's kind of the easy part, I think, because the force you're applying is given. It's 12, right? How are you going to calculate part B? What do you need to figure out first? Use logic. Come on, use deductive reasoning. What's part B? What force is acting in part B? What force is that in part B? Not gravity in part B. Look at part B. How much work is done by the floor on the desk? Oh, I can see that being if you push back with normal force, but not that way. We're saying, what else is happening? Friction from the floor. Think about moving an object. When you move an object and you slide it across the floor does work in terms of friction on the desk. So it turns out for part B, we're going to use the same formula. F d cosine theta. But what's theta going to be now? What angle is theta going to be? What's the angle of theta? We just said this in the last section. 180. Whenever it's friction, it's going to be 180 because, again, friction acts against motion like that. This was the force that we applied for the first part, Fp, a push or a pull. That's what that was. But now in part B, we have to use FF. But do we have FF? Do we have FF? Is it given in the problem? Does it tell us the friction force is? No, it doesn't. It tells us what about friction? Mu. Here, this is mu K. The coefficient of kinetic friction, mu K. That's what that value is. And that's from last chapter. If you remember last chapter, how do you find the force of friction? Before we get into the work for part B. You need the friction. The work is in the work calculated. How do you find friction? What's the formula from last chapter? Nobody remembers? Amaya? Mu Fn. Mu is 0.2. What's Fn? Come on. Figure it out. Figure it out. Ryan? What do you got? Why? Yeah, look at the weight acting down. That was the weight of the object. Wasn't that given in the problem? Go back to the problem. It said it was a 20 Newton desk. That's the weight. If it's in a vertical state of equilibrium, what must the normal force be pushing back up? What must it be for these to be in a balance? 20. This is something from last chapter that's going to carry over, this concept that if there's no vertical motion, the normal force and the weight are balanced. So we just plug in a 20 for Fn here in the formula. It's going to give us 4 newtons. That's the force of friction. And the work done by friction is going to be this formula again. Same exact formula as the previous part. Fd cosine theta, but now theta, instead of being 0, as Will told us, is 180. So we've got 4 newtons as a force of friction. The distance is still 24 meters. And we're multiplying that by cosine 180. Again, it's good to remember that cosine 180 is simply -1. It just means negate your answer. What do we get? 4 times 24. 96, right? Negative? Negative 96 joules. So, are you doing more work or is friction doing more work? What's happening here? You or friction? I mean, it's obvious. You are doing more work. Why? Sure, but from the other parts of the diagram, why else? Actually, you're right, but there's another reason I should say. Why else? How do you know that you're doing more work than friction? What else tells you that? Think back to last chapter. To do work, you have to act over a distance, right? The distance in both formulas was what? 24. So what's the difference that caused you to do more work than friction? If it's not distance, what else is used to calculate work? The distance traveled, and what else is used to calculate for work? Come on, same 2 hands. This is something I'm kind of like goading you toward. Use the formula. Think about what else is in the formula. Cosine changes it for sure. It makes it negative positive. That's a good point, but I'm saying numerically, what makes 288 bigger than 96? What's the difference here?
Well,
The force is different. How much of force are you applying here? What's this FP? How much force do you apply? 12 newtons. But friction only pushes back with 4 newtons. So as a result, if you overcome friction, what's the object going to do? It's going to move. So the net work has to be positive for it to move or accelerate or to gain velocity. So we see that the work done by you is greater than the work done by friction. If I want to find part C, and I want to find the net work done, I just take the sum of all the works. Remember the symbol? This symbol meant sum. In the last chapter, we did the sum of the forces. Now do the sum of the works. Add them together to find the overall work done. So you have 288 plus negative 96. Okay, 288 plus negative 96. 192. So the overall work done on this object between you and friction is going to be 192 joules of work. We're going to see in this chapter that we can actually, this is amazing, in section 6.2, we can turn this into a velocity. We can take this concept and see, well, what's the velocity after you do that much work? And it's pretty cool because we're going to take formulas from the earlier chapters, relate them to formulas now, and see how that works. So the amount of work you do can be easily translated into the gain in velocity. Okay, we're going to see how that works in 6.2. What I want you to recognize, though, is this. If you find the net work by you looking at the net force, you could also do this for part C. What's the net force acting horizontally? How much do you pull with this way? How much do you pull with? What is it? That's the distance was 24. 12 newtons was this way. How much was this way? 12 minus 4? 12 minus 4. 8. That's okay. 8. Now, I take 8. That's fine. 8 is the, that's fine. 8 is the net force. I'm glad you're participating. 8 is the net force, and it's acting this way. Because again, 12 this way and 4 this way, right? 12 this way and 4 this way is like 8 this way. So if I take 8 this way times 24, I'll get the same number. So again, if I wanted to think about it this way, I could think about it as follows. For part C, once you calculate part A and B, obviously just add them together. But if this were a problem on a test, and you didn't want to calculate parts A and part B to add them together, you could think of it this way. You could say, if I want to find the net work done, I could find the net force times distance times cosine theta. The net force, if you recall, was 12 plus a negative 4, because the force of friction was acting against it, times 24. Now in this case, because it's moving to the right overall, it's going to be cosine 0 still. And this would give you the exact same answer of 192. You could sum together the forces. This is the pull to the right of 12. You could take that and add the pull to the left of friction, negative 4, giving you 8. 8 times 24 will give you 192. It's the same answer, just an alternate solution. Make sure you write something like or here to show you that you can use either of these things. So again, on a test, if you didn't need parts A and B, it makes sense to take the second approach. Once you find the forces, just sum them, get an overall force times the overall distance times the direction you're moving, or the angle between the direction you're moving and the overall force. The overall force is to the right, you're moving to the right, that's why this angle turns out to be 0 here when you sum them together. Where did we take into account the 180 by doing this? Anybody pick up on it? In the previous steps with part A and B, cosine 180 played a role, which made work negative, right? Where did we take into account the negative part for friction already? It's there, just look for it. How did we already take it into account? The what? Yeah, and the net force here. What do you see? The force of friction is negative. So although we didn't use cosine 180 to do this part, it was another way of doing it. Saying like, oh, think of friction as negative, the force you're pulling is positive, sum them together, you get 8 times the distance traveled. Okay? Your homework in this is listed on the next page. Now again, I'm going to also, I already have your problem sets for 6.1 and 6.2 decided. So if you want to start on those at some point, you can also. So please, keep on top of this stuff. Take a little break before we start the next class. Stretch your legs if you need to.